Okay, good morning, afternoon, evening. I am Shiladitya Pore, and on behalf of the organizers, I want to welcome you to the first seminar in 2025 of Majorana-Raychaudhuri Seminar Series. We are truly honored to start this year's journey with Professor Rabindra Mohapatra as our speaker. Professor Mohapatra is a distinguished university professor emeritus at the University of Maryland, USA. Professor, you may start your talk now.
Okay. Thank you very much. Can you all hear me?
Yes, I can hear you.
Yes, I can. Okay, great. So I'm sorry that I had to change the time because it's 7:30
No, no,
in.
no, it is fine. It is fine.
Yes.
We are happy that you joined.
Okay, no, that's great. So I'd first like to thank the organizers for inviting me to give the talk. And what I will tell you today about is something to do with the strong CP problem of the standard model and how to solve it. Of course, we know the different ways to solve it, but I'll specifically address one particular aspect of one of the solutions to this problem. Okay. So let me just move on. And this is the work that I will describe was done in collaboration with Babu, Bhaskar Datta, and myself. So let's see. Okay. Okay, so I guess, okay, I just have to pull it up. Okay, so just as a way of introduction, I will just tell you something which all of you know, which is that the standard model is extremely successful, but of course it has got many problems and therefore everybody believes that it is incomplete. And of course, some more work needs to be done on how to improve it so that it satisfies all the problems that we face. Okay. So for example, it does not have any explanation for the neutrino mass. It doesn't have any explanation for the dark matter, inflation, dark energy, all this kind of stuff. And one of these problems is the strong CP problem, which is the subject of my talk. So, so what I will do is to first introduce what is the strong CP problem, which all of you, I'm sure, know. Let me try to shrink this one if I can. Yeah, I think so. Okay. So what is the strong CP problem? Well, if you look at the QCD part of the standard model, then what you see is that there is a CP violating term, which is the last term, which is called theta term, which is this is GZ dual and this is the strong coupling over here. And this term, once you have theory with flavor like standard model or any extension of the standard model, then what you have is a theta bar, which is the effective theta, which is the theta over here, which I denote here by theta 0, plus the argument of determinant of mu times md. So you add all of this together, and that is your effective theta bar. So if you look at this term, you see that it violates parity and it violates T. Okay. And of course, it has got strangeness 0 because these are all gluons. So this leads only to one CP violating effect, which is the neutron electric dipole moment. And of course, it leads to other kind of pi-nucleon couplings, which are also CP violating. But the bottom line is that this CP violating electric dipole moment, we know there is a measurement of upper limits on the electric dipole moment, and that tells you that the theta bar is less than 10 to the minus 10. And the question is, why is theta bar so small? And certainly there is no anthropic reason for theta bar to be small. So especially when the CKM angle is of order 1, why should theta bar be small? I think that's the strong CP problem. Now there are many solutions to the strong CP problem. Now I just wanted to mention here that my favorite is the parity solution, where you extend the standard model to a left-right symmetric gauge group. And you see that since it is left-right symmetric in the asymptotic limit, it leads to parity conservation and therefore vanishing theta. And of course, all you have to do is calculate the quantum corrections to theta. And if they are small, then that's the solution to the strong CP without doing too much. And what we have discussed before and shown is that these kind of models are easily testable in colliders. Okay, but however, my second favorite solution, which I will discuss today, is the Axion solution because it's a very interesting dynamical way to understand why theta is so small. Okay, so what is the Axion solution? Well, just to review the Axion solution, what you do is you take the standard model and add to it a pseudo-scalar field, 0 minus. This minus is not so easily visible, but 0 minus pseudo-scalar field A, and with a coupling to the gluons, which is exactly of the same form as the theta bar. So take LQCD, this is the CP conserving part, the standard QCD, and this is the theta bar part, and this is the axion part. Okay, so this was suggested by Pache and Quinn in 1977. And if you look at this term and calculate the effective potential in these theories, what they showed is that the minimum of that corresponds to A over F, which is the constant, the Pache-Quinn symmetry constant, symmetry breaking constant, plus theta bar equal to 0. That means there is no strong CP violation because this term just disappears in the minimum. Now, of course, one can see that the theory has shift invariance, which is A going to A plus C, and the shift invariance is broken by QCD instantons, which therefore break the Pache-Quinn symmetry, and that leads to the axion mass, which is roughly over a lambda QCD square over FA, where again FA is the constant associated with this axion term. Okay, and there are also matter couplings which are like 1 over FA. So that now let us see how you construct axion models. So this was first discussed by Weinberg and Wilczek, who showed that you take the gas group, GM, G standard model and its extensions, and add a global axial symmetry, which is U1 Pache-Quinn. And let some colored fermions carry the PQ charge. Now, once you have the colored fermions carrying the PQ charge, if this symmetry is anomalous in the QCD term, then through the triangle diagram right here, this is axion.
Guardando sul decreto della declaratoria non rientra. Il motivo sostanziale è che...
Sorry,
I think so. It's from the audience, sorry.
Oh, is there a question?
No, I think some issue. Not question.
Okay.
You can continue, please.
Okay, great. So A is the imaginary part of this singlet field sigma, and you can see that this diagram is anomalous, so therefore you have an effective coupling, which is A times GG dual. And this, therefore, is what we were looking for. If you look at the previous slide, it is this term which arises because of the U1 symmetry, and that therefore solves the strong CP problem. Now, there are many examples of models which solve the strong CP problem. The very first one was by Weinberg and Wilczek, who used the weak scale Higgs doublets to take the imaginary part. So the imaginary part, or the axion, is a linear combination of the imaginary parts of the Higgs doublets, HU and HD. And therefore, in this model, since this symmetry breaking cannot be more than the electroweak, we have about 174 GeV or whatever, then what you get is an axion mass which is in the keV to MeV range, and and this is a pretty strong coupling to matter, and this therefore was very quickly ruled out by K decay, psi decay, and things like that. Okay, so therefore the weak scale axion model is now ruled out. So what do you do then? Well, then there are several proposals in the late 70s and early 80s that there is something called invisible axion, which is that you break the Pache-Quinn symmetry at a very high scale, FA. And if this high scale is of the order of 10 to the 9 to 10 to the 12 GeV, which comes from cosmology, supernova, and all those kind of things, then you have a theory where the strong CP is solved and it is phenomenologically consistent. Now, of course, how do you construct such models? Well, there are generally two very well-known classes of these models. One is the KSVG model, Kim's, Shipman, Feinstein, Zakharov model, where you have the SM fermions are PQ neutral or U1 PQ neutral, but there are heavy quarks that you add to the theory which have got a PQ charge. Or there is a second class of models which is known as BFSG model, Dine, Fissler, Srednicki, and Zniski, where the SM quark, the standard model quarks, do carry PQ charge, unlike the KSVG model, where the standard model do not carry the PQ charge. The standard model quarks in the case of DFSG model carry PQ charge, and they have no heavy quarks. Okay, so therefore this is also a very interesting model. And in all these models, what they do is, just to give an example, I will look at the KSVG model. And what you see there is that you take the standard model, then you add the U1 PQ. So you add this extra term, extra symmetry to the model, and then try to maintain the whole symmetry in the whole Lagrangian. Okay, so therefore PQ is a global axial symmetry. Now you can introduce heavy singlet vector-like quarks in this theory, and denote them by capital Q, capital R, with opposite PQ charge plus minus 1. The SM quarks are PQ neutral, as I said before. So then you add the singlet Higgs sigma, which is a complex scalar field. It has a Pachequin charge too. So therefore it couples to the heavy quarks as follows, but it does not couple to the standard model quarks. So therefore, once you have you break the symmetry by giving a vacuum expectation value to sigma, denoted by Fa, then it breaks the Pachequin symmetry and gives rise to the axion. And of course, the same triangle diagram that I showed you before, we can now draw in this case, and the heavy quarks flow in the triangle. So what you have is a Q, which gives AGG dual to solve the strong CP problem. Okay. Now this is and you can do the same thing with the DFSG model, which I'm not going to describe here because it's there. All you do is take this standard model quarks and give them a Pachequin charge, and standard model Higgs give them a Pachequin charge, and then you have a singlet which then gives you the axion, and that if you give the singlet a large wave, then that is the invisible axion model. Okay. Now it turns out that there are issues with the axion solution, especially the high-scale axion solution. And one of the first things that is the main focus of our work, which is the gravity and the global symmetry issue. Okay, so one of the issues of the axion solution is gravity and global symmetry issue, which we will be dealing with in this lecture. So what you have is that there is a lore going around, and I don't think there is a mathematically rigorous proof of that, but it's certainly very plausible lore, which is that all global symmetries are broken by quantum gravity effects, and they induce a Planck-suppressed symmetry breaking term into the theory. And the question is, if you have a Pachequin model, you have a global E1 PQ symmetry, which is an axial symmetry, and that symmetry should also be broken by Planck scale effects. And the question, is it okay with phenomenology to have this kind of things? And can you still maintain that theta is less than 10 to the minus 10 in spite of these extra terms? So that is a very important question. And of course, there's a heuristic argument for why the quantum gravity should break the global symmetry, which is that suppose you have take a black hole, which is right here, and if you throw in a baryon, which is a global symmetric charge, then it goes and disappears, and then you have a one less baryon in the universe. So that means the black hole somehow eat the global charge and leave no trace of it. So therefore, there must be some symmetry breaking effect of this phenomenon in the standard model. And those must be Planck suppressed because this is coming because of the Planck, the gravity effects, okay? And you cannot do the same thing with a local charge, because if you have a local charge which goes into the black hole, then you can always use the Gauss theorem. You put a sphere around here, and then you will see the effect of the local charge which has disappeared as some field effect. Total flux will be non-zero. So you can tell for the local charge, but for the global charge, you cannot tell. So this kind of hand-waving arguments have been very convincing. And what people argue is that if you have a global symmetry, then there must be quantum gravity effects which break the symmetry. And then you have to check for the case of the axion, whether that's okay to have this kind of symmetry breaking effect, okay? So what happens? So let's take a gravity problem of a high-scale axion, okay? So the Planck scale effects induce Planck-suppressed PQ breaking terms to the theory. So for example, if you take the KSVG model, or if you take the DFSG model, in either of these models, there is a singlet field which carries Pachequin charge. So therefore, it is always gauge invariant, sigma to the fifth, and that is suppressed by only 1 power of m Planck. Okay? So therefore, what you have to do now is you take this gravity effect, and then you take the standard QCD potential of the axion, which is this term. The gravity effect gives this potential, and the axion field comes because you have a sigma whose imaginary part is the axion field. Okay, so you put this over here, then you can see that because of the sigma to the fifth, what you have got is a symmetry breaking to the fifth, and there is a Planck mass over here. This beta is the coupling coefficient of this gravity breaking term. So you minimize this term, and you want to make sure that as a result of this term, the theta must be still less than 10 to the minus 10. But since the Fa is large in the case of high-scale theories, suppose you take Fa to be 10 to the 12, then what you find is that the beta must be less than 10 to the minus 44 for you to have theta less than 10 to the minus 10. So that's ridiculous, because we tried to solve a problem which was 10 to the minus 10 level of fine tuning. Now we are generating a fine tuning which is level of 10 to the minus 44. That was pointed out in the early 90s by several papers. And that is known as the Axion quality problem. Okay. So that is the problem that we want to solve. So what is the problem? Again, just to repeat, what you have is every Axion theory must have symmetry breaking terms induced by the gravity effect, which are suppressed by M-Planck. And therefore, you must have in the potential terms which are different powers of the Axion field or the Axion wave. And you have to minimize this and make sure that the theta bar does not exceed 10 to the minus 10 in spite of the presence of these terms when you have the beta of order 1, or maybe 10 to the minus 2, 10 to the minus 3 is fine, but certainly not 10 to the minus 44. Okay, so I hope that makes the problem clear. And this is the problem that we want to solve, which is that how do you solve the strong CP problem, and yet how do you maintain the fact that the Planck scale effects do not disturb this terribly? Okay, so that's the Axion quality problem. Now, of course, there are other problems which we will not be worried about in our work, but there are problems of domain wall, for example, because once you have QCD instantons which explicitly break the PQ symmetry, they leave a G2 and discrete symmetry unbroken, and that gives rise to the domain wall problem. Unless the domain wall number is equal to 1, you have a problem which is that the universe will be totally anisotropic, and that, of course, we have no evidence for. Okay, so therefore, that's the domain wall problem. Now, of course, the Planck scale terms, which was bothering us before, could be of some help here, in the sense that the Planck scale term puts a term delta V into the potential, which symmetrizes the potential. For example, suppose you have a G2 symmetry, then you have a potential which looks like this. Follow my arrow over here. It looks like this. And then once you have the symmetry breaking term induced by the Planck scale effect, one of them goes down, another goes up. Okay, so therefore there is an asymmetry. So therefore the higher vacuum states can decay to the lower state, and that way you can solve the strong CP, you can solve the domain wall problem. So therefore, whatever the liability would in principle be an asset in solving the domain wall problem. But we will not get into this issue, because all our models that I will describe in a few minutes have number of domain walls equal to 1. So this happens only if you have more than one domain wall. Okay. Please stop me when you have any questions. Okay, so there are other issues with the inflation, other issues with the PQ symmetry, which is, for example, is the symmetry breaking scale of the U1 PQ, is it higher than the inflation reheat temperature, or it is lower than the reheat temperature? So, for example, if FA is higher than the reheat temperature, there is, of course, no domain wall problem, because the domain wall should be inflated away by the inflation. But there are the so-called isocurvature perturbations, which I cannot get into here. But that can be large and spoil our understanding of structure formation. Okay, so therefore that's an issue which you have to deal with if you have. Of course, there are ways to solve it, but that is model building, and a lot of more new things have to be put into the theory to solve that problem. So what we will do is we will stay with the F less than T reheat, which is post-inflationary PQ breaking, so that we avoid the isocurvature problem. Okay. So this is all our models will have FA equal to less than T reheat. Okay. So the question is, how do you then construct a high quality? So this is, by the way, called a quality problem. And the question is, how do you construct a model which is free of this quality issue? So let's try to outline some ways as to how do you construct high quality axion theory, so that you solve a strong CP problem, you have no Planck scale problem, and you have no inflationary domain wall and all these kind of problems. That will be really nice to have a model like that. So what you do then is, this is the general strategy, and we'll try to see how to implement this strategy. Okay. So find a natural way to make the Planck correction higher order using gauge symmetry. Okay. So we saw before that if it is sigma to the fifth over n Planck, and that's really problematic, because the coefficient must be less than 10 to the minus 44. If it is sigma to the 6, still it's not bad. It's not good, because then it's not 10 to the minus 44, but maybe it is 10 to the minus 39 or something. So in all these cases, until sigma to the 11, but sigma is the PQ field, until it reaches this level or higher, there is no solution to the quality problem. Okay, so therefore we have to construct theories where the effective Planck scale breaking term is very high order, and that's the challenge that we have to face. So it should also solve the domain value issue for post-inflation if NW is bigger than 1, but our models have number of domains are equal to 1, so we will not worry about this problem at all. Okay. So there have been a lot of, before our work, there had been a lot of solutions to the Axion quality problem. I'm not giving an exhaustive review of them, but there are some of the papers that you can look at if you are interested in this idea. There are the people have proposed that the Axion, instead of being an elementary field like the sigma field that we talked about, let it be a composite field. That means there is some preons or pre-quarks or whatever, of which the Axion is the composite. Okay. So there are examples by these people where you can solve this the quality problem using composite axion. Then there are solutions which use the mirror worlds. That means you say that our world, there is a duplicate of our world, which is the mirror world. And if you have a situation of that case, then it is the mirror world strong coupling which gets into the axion mass formula. And therefore, the axion in that case can be much heavier than the micro electron volt or whatever that is generally talked about. So that's another class of solutions to the quality problem. Then there are extra dimensional or string solutions which have been discussed by these people, and also there are discrete gauge symmetry solutions to this problem. Okay, so therefore, there are already many solutions which were proposed in the literature, but we wanted to look at it to see if we can do a sort of more conventional unified field theory kind of solution, which does not involve the compositeness or mirror world or extra dimension or anything else. Okay. So what is our strategy? So our strategy is the following. Choose a gauge symmetry, which is this usual weak gauge symmetry or the flavor group or whatever, times the U1A gauge symmetry. Okay, there is an axial U1 you put into the theory, such that the whole G and U1A are anomaly free. Okay. Now this G can be either the standard model or higher. And I will give you examples where this is the standard model. And my real star of this example is it is an SO10 theory, because that also solves other problems of the standard model. Okay. So G therefore can be either the standard model or it can be a higher symmetry which contains the SN. Now if the model has an accidental symmetry, so now you take this theory and make it anomaly free, you have quarks in them and you may have more quarks, etc. Now if this theory has got an accidental global symmetry, which is anomalous, that means the colored fermions carry that symmetry, then this can be identified with the PQ symmetry. Okay, so in other words, an interesting feature of this class of models is that the Pechequin symmetry is not put in by hand, but emerges out of the fundamental construction of your theory for the electroweak sector. Okay, I think that's a very interesting feature of this class of models. The global PQ symmetry is a consequence of the gauge theory that you build. Okay, now it's spontaneous breaking then will lead to an axion, and the U1A now is something which you can choose, and if it is chosen to push the Planck breaking effect to sufficiently high order in the equivalent sigma field, then you solve the quality problem. The idea was mentioned in the Bar-Seckel paper in 92, but they never gave any examples which are interesting. And what we have done is to construct several examples which give interesting solutions of this kind. Okay, and I will first give you a warm-up example, and then I will give you the real a certain example which we are very happy about. Okay. So what is a warm-up example that I want to give? Well, so you take the standard model, and then you take a gauge symmetry, which is U1A, but better make sure that it is anomaly free. And there are not that many examples that you can construct like that. So what we have is we introduce heavy quarks capital Q 4 of them in one model, and then the right-handed ones, they're the opposite gauge charge. You see these are +1, +1, +1, -3, and this is minus of that. So these are the opposite PQ charges that you have, not PQ charge, U1A charge. And then to cancel the anomaly, we take some very singlet fermions, like right-handed neutrinos, but there are 1, 2, 3 of them, and they have the standard model charges, which is singlet under SU3, singlet under SU2, and 0 under U1Y. So this is completely neutral under the standard model. And then you have got the U1A charges, you choose them in 2, 4, and -6. So it turns out that it is this combination which is completely anomaly free. Okay. So this is sort of accident and miracle. Yeah. And then you add the new scalars beyond the standard model Higgs doublet, call them T and S. So these are our key new fields which will give rise to the axion. Okay, so there is a T which has got a high PQ charge, high axial charge which is 6, and the S has got an axial charge which is 2/n. Okay, and all this is now out of the archive preprint, which is this is the number. Okay. Now, of course, in this case, we didn't specify what are the hypercharges of the heavy quarks, but you can either leave them free, but it is better to make them 2/3 or -1/3 so that they can couple to the standard model quarks and avoid cosmological issues, because then they can decay. If these are arbitrary, then they will not decay and they will give rise to overclosure of the universe, and that's a problem. Okay, so that you better make sure that it is better to choose 2/3 and -1/3. Okay. So what is the model Lagrangian? Well, there is got a Yukawa term. So I'm getting into a little bit technical details. I hope that's okay. So you have got a potential which you can see that because of the different charges of the T and S fields, you have got only fields of this type, T star, S star, product of this and product of this and like this. Okay, so the renormalizable part consists of these terms only, because there is no interlocking term, so-called, at the renormalizable level. So therefore you can see, you look at the symmetry and look at the potential and you see that it has got a U1T cross U1S symmetry. T because these are all singlets, S, U1S because these are all singlets. So you take this potential and that has got a U1T cross U1S symmetry. Now you look at the Yukawa term, then you can see that there is one term over here, then another term which is a higher dimensional term, then another term and another. There are 4 terms, like 4 classes of terms like this. Okay. So you can now see that the whole Lagrangian has got a U1 global cross U1 global symmetry, which are accidental, and one linear combination of these becomes the Pechequin symmetry. So how do you see that? Well, if you take the decomposition of the S and the T, this is the real part, this is the wave, and this is the imaginary part of our Fs, and this is one field and there is a second field. And you can see that there is one linear combination of the imaginary parts, eta S and eta T, which becomes the U1A longitudinal mode, so that symmetry is broken, and the orthogonal combination becomes the axion. Okay, so what you have therefore is an axion field which looks like this. And now you are ready to do phenomenology, which of course I will not do too much here because this is not there is no time to discuss this model in detail, but that is discussed in great detail in our paper. Okay. Now the interesting feature is that if you look at, since the S and T couple to quarks, let's just look at it. So you can see that the T couples to quarks, for example. So then what you have is that this axion field through the triangle graph will give rise to an anomalous coupling, and that is the one that we use to solve the strong CP problem. Okay. So now in this model, let's try to look at what is the Planck scale effect. You see that we left the charge of the, if you go back, you see that we left the charge of the S to be 2/n. So we can now start picking n, there are 4, 5, 6, or whatever. Then you see that then you see that the leading Planck breaking terms are of the form T star S3n times m Planck to the 3n minus 3. This 3 comes because the T has got a charge which is 6. So this 3 sort of cancels that, and this is the charge. And if you see n is bigger than 4, then of course this is safe from Planck scale effect. And it's a sufficiently high number because you can see 3 times 4 is 12, plus 1 is 13. So this is effectively like sigma 13 over m Planck to the, I guess, m Planck to the 9. Okay, so that's the term, and that is pretty safe. And maximum Fa that is allowed in this case is 5 times 10 to the 10 GeV, and therefore the axion mass is bigger than 1.6 times 10 to the minus 4 electron volt. Okay, so you can do phenomenology with that, but that may not get into that because I have no time for that now. Okay. So the star of this show, as I said, is the certain model, which really is a very interesting model for the quality problem of the axion. Okay. So first of all, let me just give you, for those of you who are not at all familiar with ascertain, why consider ascertain? Because it's a great unification group. Okay, it unifies all quarks and leptons of one family into one representation with the 16 spinor representation. And there are 3 generations, 3 16s, and there are 3 generations of quarks and leptons. Okay, and then the Higgs you can choose for a renormalizable model. You can choose it with 10, 126, and 210. And this is a very nice framework for neutrino masses because the 126 gives you the seesaw mechanism, and the 210 breaks the grand unification symmetry, and the 10 and 126 give rise to the quark and lepton masses. And this kind of model has been analyzed a lot in the literature in the early 2000s, and even now people are writing papers on this. Okay. So this is a very minimal model for all fermion masses, including the neutrinos. And that's very successful in describing all the CKM angles, the CP phase, and quark masses and everything. Okay. So it allows also various testable baryon violating processes. Depending on how you break a certain to standard model, the baryon violating processes, proton decay, lifetime, and so on, can have different values. Okay. So what is the model that we're talking about? Well, here is the real stuff of the model, which is in this paper. And that is that you take the fermions, the 16 spinors, this is 16, and there are 3 of them, 1, 2, 3, and the axial charge is 1, okay, plus 1. Then you put in a fermion which belongs to the 10-dimensional representation of a certain with a U1 charge which is minus 6. Then you put a singlet, which is a certain singlet, this is 1 here, and it is 12, which is the U1 charge is 12. So, and then you take the 3 singlet fermions, which are singlets under a certain, these are sort of like right-handed neutrinos, but not the right-handed neutrino of the 16 spinor. So these you put in with U1 charges minus 4, plus 8. Again, this is a miraculous set of numbers here. If you calculate the anomaly, it just cancels out, including the cubic anomaly. That's in some sense, the main part of the work. And then the question is how to analyze the phenomenology of this. Okay. So just I want to repeat again, you have 3 16s, which are the 3 generations of quarks and leptons. This is one extra field, which is F, which is sort of like the KSVG singlet fermion. But now because it is a certain, it's part of 10. And then the real singlet fermion, which is U1 charge is plus 12. Okay. Then you want to break the symmetry down to the standard model. So what are your fields that do that? Well, there are some 45 and 210 fields which are neutral under the U1 charge, which break the grand unification symmetry. Then you got a Higgs, which is 10, which is U1 charge is minus 2. So it can couple to 16 fermions, psi F, psi H. So that's the fermion over here. And there is a real 10, which is the U1 charge 0. Then the delta bar, which is the singlet, which is the 126, which does the seesaw and also contributes the quark and lepton masses. That is minus 2. And then there are 2 singlets, T and S, which has got charges plus 1 and plus 12. These, by the way, do not contribute to anomalies because these are all scalars. Okay, so the anomaly part is taken care of here. And this is just to do the symmetry breaking. Okay. So this is all in this paper, and what are the now I'm going to describe some more technical details about this model. So there are two things you have to write down once you start constructing this kind of model. By the way, this technique, you can also start thinking of models of this type. We haven't exhausted all the models that could possibly be constructed, but you can start thinking, and this is the technique. First you construct, take your gauge group G, and then add to it the gauge group U1A, and then you move on and construct the theory to be anomaly free. And then you write down the Yukawa coupling and the potential. Now you can see that this is the Yukawa coupling of the 10, which is H, which is the 16, 16, 10. This is the 16, 16, 126 bar. It's right here. This is the 10, 10 singlet S. And then these are the singlet, singlet, and there are the singlets. Okay. So this is the Yukawa coupling, which has got all the U1A invariant as well as a certain invariant. And then there is a potential which looks like this. And the key term in the potential is this one, which you can see. All the rest are sort of renormalizable. And we'll see that I have not told you what is the accidental U1 group here, but you can see that this will be the one that is crucial for our consideration. That will be the Planck scale term that we'll worry about. And you can already see that this is a Planck to the 9. Okay. So just to give more details, these are the terms that give rise to the quark, lepton, and neutrino masses, and all the rest are for the Pacheco symmetry. Okay. And then let's try to look at the global symmetry of this model. Okay. The global symmetry of this of this model is that so these are all the gauge charges. We have no freedom here, but this is the global symmetry that we notice this model has, which is +1 for the 16th, 0 for the 10 fermion, 0 for the singlet fermion, and 0, 0 +2 for the right-hand neutrinos type fermions, the singlet certain singlet fermions. And then you have got the 10 scalar, the 126 scalar, and the T. They have got non-zero charges. -2 is +2 and +1. Okay. So that is again the second key part in this kind of model building. That is, you take the theory, first construct an anomaly invariant, U1A invariant gas theory, and then you look for accidental global symmetry. You may be unlucky, you may not have an accidental global symmetry, but this model does have one, and that will be our Pacheco symmetry. Okay. So you try to now identify the axion field, which is a lot of dirty work that you had to do. And what you do is take each scalar field, write that into a real part and a vacuum expectation value part. You can give it a phase, it doesn't really matter. Then you have got the pseudo-scalar part divided by the vacuum expectation value. So you take this thing, we have got many fields, we have got H, we have got H prime, we have got delta, T, and all those things. So all of them have such a decomposition. So I goes over all those scalar fields. And then once you get this, then you can take all the fields and calculate which is there are several fields which become the longitudinal modes of the gauge field. And then there is one field which you can identify the axion. And the axion is, you can see it consists of the imaginary part of the scalar field S, imaginary part of T, imaginary part of the 10 fields, etc., all those kind of things. Okay. So this is the axion. So once you identify the axion, then you have the FA. You can calculate from these are all very lot of detailed work that goes into this, but you can calculate the FA, and you calculate the thing that is important. I will emphasize later that there is a ratio of the scalar wave square over the T wave square, which is an interpolating parameter between the KSVG, DFSG. So I didn't emphasize it yet, but it turns out that this model is not like the KSVG model or not like the DFSG model. It's an interpolating model. It sort of connects the two through this parameter R, as I will emphasize later. So let's now look at the quality constant. So if you look at this theory, and you can see that this is the one that gives rise to the quality problem, and you just find the theta bar, and you see demand the condition that this minimum of the potential gives rise to a theta bar which is less than 10 to the -10. Okay. So once you do that, then you see that you have the FA and the VT. You can go all the way up to, I will show you pictures of these. You can go all the way up to 10 to the 11 GeV. Okay. So now it was pointed out to us by Susik that there are also another kind of effect that is important in this theory. And that is there may be less Planck suppressed effects which do not directly contribute to the theta bar, but through loop effects they can contribute. So in our certain model, such an operator is the 10-6 singlet m Planck to the cube. You can see this is m Planck to the cube. So this is not sufficient suppression, but this doesn't contribute to theta bar. So that's okay. But once you have some higher order diagrams, loop diagrams. So we found that if you take this type of term, and through such a complicated loop diagram, it does contribute to the quality problem. And you can see that you have got Planck cube times gut scale to the sixth. We evaluated this and we found this kind of an expression. And this mu to the sixth is a problem. So that requires that you must make kappa, the coefficient of this term, smaller. But it turns out that 10 to the minus 3 is good enough. So we are happy with that because this is not like 10 to the minus 44 or 10 to the minus 38. This is a reasonable amount of smallness of the kappa term that solves the quality problem. But this is an important point to remember in all models that you consider. So now let's get into the phenomenology of this theory. And so what you have is a quality. So you have got the quality constant and you have got all these constants coming from the loop effect and the higher dimensional terms. And then you plot it as a ratio of Vs over Vt, which is our interpolating parameter. And the Fa, what we found is that we must have Fa less than 4 times 10 to the 11 GeV, and Ma that corresponds to 14 microelectron volts. Okay. So this is our phenomenology. When we try to find the region where the this axion of our model becomes the dark matter, that restricts the Fa to be somewhere around several times 10 to the 10 to several times less than 10 to the 11. Okay, so this black band area is the region which is the dark matter, and that is, we use the calculation of this paper to take this line. Okay. So then we try to look for the prediction for the axion coupling, and what you have is the axion couples to various particles in the standard model, the photon, the gluon, and then it couples to the electron, and it couples to the neutron and the proton and so on. And those are the experimental parameters that you can use to check the theory. So what we found is that this is like the standard DFSG model. It's like 0.75 Ga gamma gamma over Ga gluon gluon. Then you made a plot of this over here. And this is the range because this shaded region comes because you've got different waves in your parameter space. As you vary them, this is what you get. Okay. So this is the prediction of our model. This is prediction of the DFSG model, KSVG, and there is a DFSG2, which is way below. We don't even get near that. Okay. Similarly, you can do for the proton-neutron coupling. What you have is, again, a DFSG, and here are the predictions of our model for the CAP and the CAN, the axion coupling to proton and the axion coupling to neutron as a function of Fa and as a function of Fa. So these are the band. This is the band in which our predictions lie. So if you're outside this band, then our theory will be ruled out. But if you're within this range, of course, it is okay. So the one important thing that I want to emphasize is the hybrid nature of the axion. Okay. So you can see that the model interpolates between KSVG and DFSG, and the interpolating parameter is R, which is VS square over VT square. The way to see that is that the axion is, if you go to the limit of large values of this, which is always true compared to the weak scale, then what you find is that the axion is an imaginary part of the S field, the eta S, minus square root of R eta T. So you can see that there are two limits. If R goes to 0, then the axion is predominantly S, which is the KSVG type. And if R goes to infinity, the axion is predominantly T, which is like DFSG type. Okay? So this model has a very interesting property. We don't know of any models which does that, but this model interpolates between the KSVG and DFSG. And you can see that also in the couplings, because this is the electron coupling, this is the proton coupling, this is the neutron coupling, and you can see this R parameter right here. So you can see R goes to 0, the CAE is 0 as in the KSVG model, and R 0.47 as in the KSVG, and so on. And R goes to infinity, this goes to DFSG type model. Okay, so that's a very interesting thing. And we try to correlate the observables for the two limits. So this is our theory. The yellow points are our theory. This is the KSVG limit, the DFSG1 and DFSG2. The DFSG2 is far away from our prediction. Okay. So these kind of experiments, these kind of things people are trying to measure, and the experiments sensitive to these couplings are the CAST, PANDAX, and all kinds of experiments listed here. They will be sensitive to these couplings. Okay. Now there is one other thing that I want to point out. I think my time is coming to an end in another 10 minutes. So the formula to calculate the NDW, we use this paper, and what we found is that in all our models, the number of domain walls is 1. So we don't have a domain wall problem. Okay. Now let me just mention a little bit about the other phenomenology of the model. As I mentioned, this is a very interesting model anyway, which was being considered before, not with the 1A, but just the ascertained model with 10 and 126, which was being considered widely discussed before in the literature as a fit to the fermion masses and to unification and prediction of proton decay. Okay. So what we do is for the phenomenology, which is not our work, but this has been done before. There are many papers, but I'm using the results of this paper. Okay. So what you have is a certain from either the 45 or 210, you break it down to the 224, and then what you have is a delta by the 126 wave, which gives rise to the seesaw mechanism. And then the T and S have their waves around the scale. So that does break the Pechak symmetry. Then the SM, and then you go to the SU3 plus U1. Okay. So this is the chain of symmetry breaking, and the unification works with intermediate scale around 10 to the 13 GeV, and the type 1 seesaw for neutrino masses and the quark lepton masses. Okay. So here is the unification running of this model, which is in this paper, which is that you start with this, then you go to that, and of course, in this case, you find a unification scale which is a little bit lower than what is we can tolerate. So what these people did is to put in some threshold effects and so on, so that they could push the unification scale to 10 to the 16 GeV. And that is interesting because that predicts an upper limit on the neutrino, upper limit on the proton decay to E plus pi naught mode of something like 10 to the 35 years. Okay. So in principle, this class of models of a certain type, regardless of the Pechak symmetry or not, the U1 asymmetry, these kind of models can be tested in the proton decay experiment. Okay. So there are other things you can also talk about. One is the baryogenesis, for example, the standard baryogenesis mechanism of the right-handed neutrino. This is not the singlet neutrino, but right-handed neutrino, the decay to do leptogenesis, and these sphalerons converted to baryons. The axion, of course, is dark matter. And you can also do inflation in this model, by the way, by taking one of these S or T fields and doing non-millimole coupling to gravity, you can do inflation. So except for dark energy, this model can account for many of the deficiencies of the standard model, of course, including strong CP problem. Okay. Now, there are many experiments looking for this kind of axion, not necessarily this kind, but looking for the axion. So once the results of these bunch of experiments show something, that will have implications for this model. Okay. So now I'm at the end of my talk, so let me just give a summary of what we have outlined. So we have outlined a strategy for solving the equality problem in the axion. So the strategy is that you take the gauge model you want to consider, supplement it with a U1A gauge symmetry, axial gauge symmetry, and then look for the U1A and the G must be anomaly free, and you look for an accidental global symmetry in that theory. Okay. So once you've identified an accidental global symmetry, then you are ready to do axion. Okay. Then you can look what kind of limits you are getting and what kind of phenomenological implications the theory has got. Okay. So what we have done is to look at this strategy, and I discussed two models. One is a pre-GATT, just the standard model extension, another the ascertain, and the ascertain one is particularly exciting, I think. So that's a realistic high-scan ascertain axion model, which has no quality problem. Okay, the model extrapolates between KSVG and DFSG, and it is testable in many of these experiments. Okay. So I think I'm done with my talk, and I can now open for discussion, and you can ask. I had some comments on the domain wall, but we have domain wall equal to 1, so I will not get into those. Okay, thank you very much for listening.
Okay, thank you, Professor, for a nice talk. So if anyone has questions, please feel free to unmute yourself and ask.
Hello.
Hello, yes.
Yes, yes, it's Arseny. Thank you very much for this very really nice and clear talk.
Thank you.
I have two questions. One question, so in your construction you have two complex scalars, S and T somehow responsible now for the breaking of this Pichet-Queen accidental symmetry. So is it absolutely impossible to construct something similar with one complex scalar?
Actually, we tried with 1 and it didn't work, because with 2 it is very simple. All you have is, you can see, we have things like TT star and SS star. And then you just take products, and still you have the U1 cross U1 symmetry. If you have 1, I don't know, you will have only 1 U1 symmetry. And I don't know whether in the case of SO10 we'll have or not, but for the subtle before SO10, it's difficult to construct with one single scalar. But we just have outlined a strategy and given some simple examples, but maybe worth trying.
I see, thank you. And the second curiosity that you mentioned also other approaches to solve this quality problem, and you mentioned something like discrete gauge symmetries. So which kind of groups are those?
Those are generally some GN groups.
So some abelian symmetries.
No abelian symmetries, right?
Okay, I see. Okay, thank you very much.
Okay, sure.
Are there any more questions? Please unmute yourself and ask.
Yeah, can I
Yes, you can ask, but we cannot hear you clearly.
Yeah,
We still cannot hear you. Maybe you can type the question in the chat. Hello.
Yeah, I'm here.
No.
Yeah, I think you can type it in the chat and I will try to read it.
Shantan, can you type, please? Hello, Shantan, can you hear us? Okay. So, are there any more questions? Shantan, can you hear us? Okay, Saurabh Shukla, you can unmute yourself and ask.
Oh, there is a chat. Let me look at the chat.
Yeah, will the sushi version of this model also work?
Sushi, I have not tried, and I think that's a very interesting question. One should try it and see. But sushi, of course, has got many more fields, because the delta will have a delta bar field and things like that. So, but it will be interesting to try and see whether that works. We haven't tried that. Let me see the chat. Oh, will sushi version. Okay. Yeah.
Okay, Shantan typed a question.
Yeah,
I was wondering if you have any comments on string theory.
no, I have no comments on string theory constructions of these models. But of course, we know that the string theory always leads to many axions, and one of them could be used for strong CP problem. But beyond such general comments, I have nothing specific or illuminating to say.
So this type of axion should satisfy the axion monodromicity or Dante Inferno, which string theorists are interested. So that's what I was just wondering.
I think I missed the main part of your question. Can you repeat it a little slowly, maybe? Let me see the chat. Maybe put it in the chat.
Shantan, you
hello,
can.
sir. Yeah,
Yes,
can
we
you
can
hear
hear
me?
you.
Yeah,
Yes.
yeah. So I was just asking that in string theory, there are some constraints on the axion model, right? Say axion monodromicity or the Dante's Inferno. So I was just asking that this SO10 would satisfy all this. Like, would it be consistent with the monodromicity of the complex plane or something like that? So I was just
I think so. I think so. I think this is consistent with everything that we are familiar with.
Yeah, thank you very much for this talk, sir. Actually, I was in auto, so like the net was very difficult to get. Sorry. Yeah.
Okay.
Are there any more questions?
Maybe if I can ask another
Yeah,
one.
of course, you can ask.
So is it kind of straightforward that number of domain walls is always one in this construction?
That's a very good question, actually. We just calculated and we found it to be one, which we are very happy with. And there is that formula in the
This Ringwald
tamarit and paper. But sort of intuitively, I cannot tell because there are more fermions and yet we see they have domain 1. I think it's a conspiracy between the KSVG model, which has got domain 1, and the 16. I think there's something is going on there. But it will be interesting to unfold as to why this suddenly, in spite of so many fermions, the domain 1 is 1.
Okay, I see. Thanks.
Sorry that I don't have a better answer.
Yeah, no worries.
Okay. Are there any more questions? If so, please ask. Unmute yourself and ask. Okay. So if not, then let us thank Professor Mohapatra for joining us today. And we are really grateful to Professor Mohapatra for joining.
Thank you very
Thank you,
much for
Professor.
inviting me. Thank you.
And Professor, would it be possible to share your slides? We will keep it
Yeah,
on the seminar.
Yeah, I can send them to you.
Okay. Thank you, Professor. Thank you for joining.